So we know that vectors have both a magnitude and a direction. What I want to do right now is just focus on the magnitude for a moment. So let's start with an example in 2 space. Let's suppose I've got the vector v is 3, -2. If I want to talk about the magnitude, that's also called the norm, and both of those are just fancy words for the length of the vector. I can denote that one of 2 ways. I can put the vector inside these double vertical bars, okay, or you'll also see it written inside of just single vertical bars. It almost looks like an absolute value. I know that means magnitude, not absolute value, because what's inside of the bars is a vector, not a number. Okay. So some textbooks use the double vertical bars. Our textbook actually uses the single vertical bars, but you'll see both forms of notation. I prefer the double vertical bars. That way I just don't get confused with thinking it's an absolute value. And that's what I'm going to use throughout the semester. Normally I try to match the textbook, but last semester my students told me that they also preferred this, so I just went ahead and used that. That's my preference, and some of the videos for this class I created last semester, so they're going to use this notation. So I'm just going to be consistent. I'm going to use this notation. You're free to use either. You need to recognize as you're reading the text that this means the magnitude of a vector. Okay, so how would I calculate this? Well, I'm going to draw myself a picture. Now I can put v wherever I want, but it's often convenient to put it in standard position. So if I put it in standard position, the tail is at the origin. We're going 3 over and 2 down. And what that means is that the tip is at 3, -2. Okay. So we're looking then at the distance between the origin and the point whose coordinates are just the components of that vector. Okay. So remember, I can think of this vector as being the position vector for this point. It's the vector that, when it's in standard position, points to this location, 3, -2. But I know how to find the distance from a point to the origin, so I can say the magnitude of v is just the square root of 3 squared plus -2 squared. So that's going to be the square root of 9 plus 4, or the square root of 13. Same thing works in 3 space. Now I'll do an example in 3 space, but I'm not going to worry about drawing the picture. Let's just say I've got w is -2, 4, -3. Well, if I were to draw that in standard position, its tail would be at the origin, and then its tip would be at the point -2, 4, -3. Okay, so this is the position vector for the point whose coordinates are the components of the vector, -2, 4, and 3. And I know how to find the distance from a point to the origin. So this is just going to be the square root of -2 squared plus 4 squared plus -3 squared. And of course, once I square things, the negative signs just drop out. So this is going to be the square root of 4 plus 16 plus 9. That's the square root of 29. Okay. So in general, in V2, if V is V1, V2, the magnitude of V is just the square root of V1 squared plus V2 squared. In V3, the space of vectors in 3 space, if W is W1, W2, W3, the magnitude of W is the square root of W1 squared plus W2 squared plus W3 squared. Okay, so I can calculate the magnitude of a vector. I want to talk now about unit vectors. Unit vectors are very, very useful. Unit vectors just means that the magnitude is 1. So the length of my vectors is 1. Unit vectors are great when I want to use a vector to indicate a direction, but I don't want the length of the vector to complicate or warp my results when I do calculations. So if I'm using a vector just to determine a direction, very often I'm going to choose to use a unit vector to do that. Okay. So that just means, again, that the magnitude is 1. Now, let's suppose I have this vector 3, -2. Now that has a magnitude and a direction. We actually just calculated that the magnitude of v was the square root of 13. So this is clearly not a unit vector. But if I wanted to have a unit vector that pointed in the same direction, I could create one. The process of doing that is called normalizing. So when we normalize a vector, we preserve the direction, but we change the norm, or the magnitude, to make it a unit vector. So if it was too long, which it is in this case, I'm going to shrink it to make its length 1. If I have a vector that's shorter than 1, I would stretch it to make it 1. Okay. So when I do that, what I'm going to do is, to preserve the direction, I'm going to just take a multiple of this vector. A positive multiple of this vector will preserve the direction but change the magnitude. And if right now the magnitude is root 13, I'm thinking what I want to multiply by is the reciprocal of root 13. I'm going to scale it by that amount. So I started with a vector whose length was root 13. I shrunk it by a factor of 1 over root 13. I should now have a unit vector. Let's double check. So if I do the scalar multiplication, this becomes 3 over root 13, -2 over root 13. I'm going to consider it optional to rationalize this. Totally fine to keep the roots in the denominator if you want to. You should certainly know how to rationalize. This would be the same as 3 root 13 over 13 and -2 root 13 over 13. I'm not super picky about that, simply because many of the problems we're going to be doing are fairly long. And on timed exams and quizzes, I don't want you spending a lot of time worrying about simplifying. I want you to show me that you've learned the multivariable calculus that we're studying this semester. Okay, so let's double check. Now this is a different vector from v. It doesn't, so I can't call this vector v. What I can do, and this is some notation that I'm going to use throughout the semester, although the textbook does not use it. So I'm introducing that here, and I'll use it throughout the semester. You're welcome to use it. For some reason, our textbook doesn't. What I've done is I put a little hat on it. Okay. So I'm using the name v, but it's not v, it's v hat. Okay. V hat is v normalized. I've shrunk it, in this case, so that its magnitude is 1. And if I were to double check, the magnitude of v hat is, let's just check, that would be the square root of, let's actually work with this version. I think that's going to be simpler. If I square this, this is going to give me 9 over 13. Plus, if I square this, this is going to give me 4 over 13. Oh my goodness, that's the square root of 13/13, which is 1. Okay. Kind of nice. Okay. This actually illustrates a fact about how scaling a vector affects the magnitude. Scaling a vector, if I'm scaling by a positive number, I'm just going to multiply the magnitude by that number. I do need to be careful though, because scalars are allowed to be negative. Okay. So let's suppose that I have v is a vector in n space, and let's suppose that k is a real number. K is a scalar. And I want to talk about what is the magnitude of k times v. Okay. Now, a lot of times people are going to want to say, oh, I'm just scaling by a factor of k, so the magnitude should just be k times the magnitude of v. That's not correct, because I don't know whether k is positive or negative. But I do know that the magnitude, or the length of a vector, is always positive, non-negative. It could be 0 if I have the 0 vector. Okay. So what this will be is the absolute value of k times the magnitude of v. Let's actually prove that. Let's say we're working in two space. Let's let v be v1, v2. Let's let k, so this is in v2, we'll let k be a real number, and let's just calculate the magnitude of kv. So that would be the magnitude of k times v1, v2. That would be the magnitude of kv1, kv2. Oops. Just doing the scalar multiplication. So that's going to be the square root of kv1 squared plus kv2 squared. Now, I can just say that's going to be the square root of k squared v1 squared plus k squared v2 squared, because exponents do distribute over multiplication. So I'm just squaring both factors. Now I can factor out a square root of k squared, and that's times v1 squared plus v2 squared. Okay. Now, square roots distribute over multiplication. Let's see, I need some space. So I'm just going to continue over here. So I can say that's the square root of k squared times the square root of v1 squared plus v2 squared. Okay. Here's where I need to be very careful. A lot of times people want to say the square root of k squared is k. That is wrong. The square root of k squared is the absolute value of k. Imagine if k was negative. If k, just off to the side here, if k was negative 3, k squared would be positive 9. The square root of k squared would be the square root of 9, which is 3. It's not k, it's the absolute value of k. Okay. And then this, of course, is just the magnitude of v. So we're taking advantage of that when we use this process of normalizing a vector. If I have a non-zero vector, okay, if v is not the zero vector, we can define v hat to be the unit vector in the same direction as v. And what we did is we got that by simply scaling v by the reciprocal of its magnitude. You'll often see that written like so. This is just scalar multiplication. We're dividing by the magnitude of v, but that's doing scalar multiplication. That's scaling by the reciprocal of the magnitude of v. The book is going to use this notation. This is a little bit shorter to write, so you're certainly welcome to use it. You can write it this way if you prefer. It's up to you.